Ben bonjour à tous. Donc aujourd'hui, on a le plaisir d'accueillir Ayman Saïd, qui nous CNRS et de l'Université de Reims, qui va nous parler de l'apparition des petites échelles dans l'R2D.
Merci beaucoup. Thank you all for being here. Je vais faire en anglais. Ça, voilà. It's a pleasure and honor to be here. So today we're going to talk about small-scale creation in two-dimensional perfect fluids. Everything I talk about today is in collaboration with actually my thesis advisor, Thomas Lazare. I had never worked together before. It's the first time we worked together. So for me, 2D perfect fluids is exactly the 2D Euler equation, which today we're going to mostly work on the torus, but sometimes we're going to work on R2. So in this case, the 2D Euler equation is simply the vorticity is given to a transport equation by its own velocity. The velocity field is being determined between the stream function that in return being determined from the vorticity through a Poisson equation. Gradient orthogonal for me is going to be minus dx cubed psi dx times psi. And of course, because we're on the torus, for this to make sense, we're going to always work with the zero average, omega being zero average, which of course is transported by the flow. Again, formally, we can, this is a transport equation. So we're about to define the flow map, the Lagrangian flow. And well, not talking about regularity or anything yet, formally at least, the solution omega of t is given by omega of 0 pulled back by the flow. So formally at least, again, we have U is a gradient orthogonal, so of course U is divergence free. So the flow here is of course volume preserving. In particular, LP norm of the vorticity should be propagated. And the standard theory for well-posedness for this equation is given by the Udovich theorem, which I think happened in the early 60s, and it goes as follows. For bounded vorticity, there exists a unique solution to the 2D Euler equation that is weakly continuous in time, values in L infinity. The weakly continuous part is simply because this is a transport equation. There is no hope to have anything more than weak continuity in the L infinity topology. And we also have propagation of smoothness for all s bigger than 1. The HS norm of the vorticity and the HS plus 1 norm of the flow is being propagated. And it does so a priori double exponentially fast. Here it's an extra derivative on the flow because the velocity field is one derivative better than the vorticity. It is surprising that you have this double exponential here at first. One is used to the Grandval inequality, you always expect exponential. But note here that for bounded velocity, for bounded vorticity, the stream function is not C2, right? This is there is the failure of inverting the Laplacian on C2. But of course, it is what you can show is for bounded vorticity, which is the uniform bound being propagated, we have log Lipschitz velocity. Then you can do all the computations by hand, and then instead of having the Grandval with exponentials, you have the log Lipschitz Grandval, and the bound you get is double exponential. On the torus, the optimality of this bound is completely open. This is completely open on the torus. And it is a famously hard open problem in the field. On the disk, there is a celebrated work by Jacques-Louis and Kiselev. It's a 17-page paper in the Annals of Math. It is beautifully written, and I recommend anyone to read it. It is like a small dessert. It's a really nice paper. And they use the mechanism identified by Father Bahouri here and Jacques-Louis in the 90s, which is the following vortex patch. I'm just drawing it on the torus. So this is called the Bahouri-Schumann patch. And the idea is that here you have a hyperbolic point. And then because of this jump here, the hyperbolic point saturates the log Lipschitz nature of the velocity from the Biot Savart. Of course, they do it on the disk, so they use something like this, plus minus. But the mechanism is the same, and the use of the boundary is key because the point where most of the growth is happening is being completely fixed by symmetry. Once you remove symmetry or boundary, it's not at all clear how to fix a hyperbolic point in a way to get this double exponential. So the goal today is I'm going to just try to present what are the interesting equations and questions we look at on the 2D Euler equations and the interesting open problems. The only known result here is due to Denisov, and it only shows superlinear growth. Linear growth is known due to the works of implicit damping, that I'm going to talk about later on. And getting linear bound is fine. And just superlinear with no quantifiable bound was done by Denisov. Other than that, in the smooth case, the problem is completely open. Now, what's the picture? What's really happened? Most numerical or physical simulation show something like this. So the colors here are going to be the level sets of my initial vorticity. So I'm just taking some random function. There's whatever kind of level sets you have initially. And I'm kind of observing the infinite time limit is the following thing happening. The fluid seems to reorganize itself, both at the small scales and the large scales, towards some simpler states. So the 2D Euler equation is a non-local, non-linear transport equation. This is actually cheating a little bit because in any of those experiments or numerical simulations, if you zoom in a little bit here, you really see this kind of picture. And the limit here should be in a weak sense. One could make such a conjecture rigorous. And this was done by Schnellmann and Schwerer. It has to do with the generic compactness of the omega limit set and the generic loss of compactness, so mixing the infinite and time limits. I'm not going to talk about this today. Maybe at the end, if you're interested, I can talk about it. But there is there's a very beautiful physical picture, but there is a rigorous mathematical conjecture one can make to try and make this picture rigorous. The conjectures are due to Schwerer and Schnirelmann. There are special cases where we know that this picture holds true. Of course, the celebrated works. So the first one actually is the Landau damping, but for the Vlasov equation. So the celebrated work by Villani and Moreau. Then for Euler, this was done first by Bedrosian and Masmoudi, and so near shear flows. So they work near this picture here, and they say if I take those end states and I perturb them a little bit, the picture still holds true. So usually it's just shear flows. And then it was by Howe and Gia and Masmoudi and Zhao. There is only one other type of works that are known where you go from this picture to this picture. And but when you work in a special class of solutions under symmetry. So if you're familiar with the soliton resolution conjecture in dispersal equation, this is the analog of the soliton resolution conjecture, but for the 2D Euler equation. We know that Euler comes with infinite families of steady states, infinite dimensional families of steady states. So this is the adapted version of this conjecture to the 2D Euler equation. And as we do for the Schrödinger equation, but sometimes we restrict ourselves to radial symmetry and then to try and solve this certain resolution in some special scenarios. For the 2D Euler equation, we can put ourselves into two special classes of symmetries. One is called the scale invariant solutions. So using the scaling symmetries of Euler, there is a special class of solutions called scale invariant solutions, or combining the scale invariant symmetry to rotations, we get what we call logarithmic spirals. And those two special cases, the conjecture has been established due to the observation of some special Lyapunov functions. This was done by myself with Tarek Gindi and Ryan Murray for scale invariant solutions, and with Inji Jung for logarithmic spirals. But that's not what I'm going to talk about today. It's just the general picture of the field. What I'm going to want to talk about today is the following. See, the vorticity is being transported. So topologically, the topology of the level sets are conserved in finite time. But in order to go from this picture here to this picture here, I have to break the topology of the level sets. So the conjecture by Yudovich is the following. The conjecture Yudovich in the 70s, I think it's 74 if I'm not mistaken. So generically, the set of vorticity such that the supremum of, say, a nabla omega of t at infinity. So generically, this holds true. And time is equal. Of course, the hard part here is to try to understand what generically means. Extremely vague. In all of the results I talked to you about implicit damping or forcing the fluid to equilibrium in special symmetry classes, the results are usually for everyone in a neighborhood of a steady state, or everyone. This, of course, completely avoids the generic question, right? It doesn't. Of course, everyone is a very good answer to generically, but it does not really put the finger on where is the difficulty there. And there are a couple of scenarios where this can be answered. First by Yudovich himself in the 90s, and the same thing a little bit generalized by Murgulis, Schneerman, and Yudovich a little bit afterwards. So what did they show? They show that if you work in a domain omega, where you have part of the boundary that is flat, then the conjecture actually is also for everyone. It's almost everyone. So the conjecture is true, and here generically, you don't really make it quantitative, but let me say this. Written by Russians in the 70s. So what the exact statement is, I cannot give. But the only thing I can say is when there's a flat portion of the boundary, there exists a Lyapunov function that causes growth. But this conjecture in the case in the following case so we're gonna for m-fold. So n-fold are just the solutions that are invariant by rotational angle 2 pi over m. So m-fold symmetric solutions, so m-fold symmetry. So if we work on, say, C1m of S2, then the conjecture is correct. The conjecture has been proven, conjecture has been established, and this was done by holds true. And this was done by El-Gindi Murray and myself. And the observation is actually pretty simple. It is the following. So here generically has a very precise sense. So here, going to be G delta set of initial data. So here, generic in the sense of the bare category, an intersection of open dense sets. And what's the observation? The idea is that in M-fold symmetry, so in M-fold symmetry, say fourfold, if I draw a fourfold symmetric solution, the north pole and the south pole are fixed. And the scale invariant solution I talked to you about, the scale invariant class of solutions I talked to you about, actually describes exactly how the north pole and the south pole turn on themselves. And you can show that persistently they will turn in different directions, generically speaking. And if you try, so if you draw a imaginary line from the north pole to the south pole, it's going to spiral. And it's going to become of infinite length. In particular, what we're able to show is that for a dense set of initial data, we have that d phi t L infinity blows up. This, of course, does not tell you anything on the vorticity yet, but I'm going to show you today how to go from the Lagrangian instability, so this is the instability on the flow map, to the instability on the vorticity. And so I'm going to present two results today with Thomas. And the first one is the following theorem. So this is Alazar. But before I present this, I'd like to note that using a boundary or a symmetry is essentially the same thing from a point of view of the analysis. And so here is a result without boundary, but it is a little bit cheating, and I'll explain why. For S bigger than 1, the set of vorticity omega 0 in HS such that the supremum in time of the HS norm equals plus infinity is G delta in HS. We are on R2. This is the first result. So this completely answers the conjecture in the case of R2.
Is it the gradient or
What?
is it omega t or gradient?
Omega t in HS. This is the HS law.
Okay.
Yes. The L2 is conserved, of course, and it's the HS that blows. And I claim that this result, while there is no boundary to R2, there is still some sort of boundary. And the boundary is just at infinity. Particles at infinity do not move. And that's the trick here. So here, I essentially used that the North Pole and the South Pole were fixed points. And I used the fact that I can understand really well how the fluid moves around those fixed points. In the case of R2, for finite energy solutions, it's actually almost the same thing, but instead of having the North Pole and the South Pole, what's really happening is that the point at infinity is being fixed. So my goal today is try to communicate ideas how to prove such solution, this type of result. I'm going to talk about the result about it on the torus in 20 minutes. But before I get into the proof, are there any questions? How would one prove this result? All good? Okay. Either a very good signal or very bad. There you go. So usually there are 3 steps to this proof. The first step is to show that the set of omega 0 in HS such that So set of omega 0 in HS, so that the supremum in time of the flow blowing up is this. This is the first step. This is the first thing we want to prove. On the circle, on the sphere, this is what we were able to do. But now I need to show why is this true on R2. Okay, so this is usually the first step. The second step is how do you transfer the Lagrangian instability to vorticity instability. The second step, I'm going to explain how we show the first step, but afterwards, I want to explain the second step first. So this is a Lagrangian instability argument. And this is due to Koch. It was done in the 2000s, I think it's 2004. I'm gonna write down the statement as I understand it, because all the ideas are there in his paper, for sure. Just that the statement is not so clear. So you take omega 0 in HS, such that the supremum of the flow grows so the flow grows unboundedly. Then, for all R strictly positive, and for all thresholds N, there exists a initial data that is arbitrarily close to the vorticity, such that the supremum of is bigger than N. I'm going to also explain how to prove this in a second. But before this, I'd like to show how, once we have points 1 and 2, we can prove the full theorem. And this is due to a bare category argument. And this is due to Henny, which was actually, I think it's Patrick Gérard, who used it in one of his papers, and then explained it to Tarek, then explained it to me. All this to say, it's good to share ideas. Helps me solve problems. So the idea is, if you consider for N and N, the following set, so the set of F in HS such that the supremum with T in HS went above the threshold N strictly, then what can we say on this set? What can we say on this set Bn? Well, the solution map of the Euler equation is continuous on HS, so Bn is open. It's just by continuity of the solution map of the Euler equation. And if I can show point 2, it's dense. It's dense. But if I consider the infinity, the intersection with the N, by the bare category theorem, B infinity is G delta. But B infinity is exactly what I'm looking for. B infinity is exactly the people for whom the HS norms grew unbounded. So I hope you're now convinced that in order to prove this, I need to prove those 2 points, points 1 and 2, and then I'm finished by the bare category argument. Suppose someone came and gave you for free point 1. Let's try and prove point 2. The idea is the following, right? The Euler equation is a transport equation like this, and the flow solves this. Particular for two different solutions, we have the following difference estimates. The difference between omega t prime minus omega t in HS is always smaller than, so this is standard hyperbolic estimates, and infinity. Some constant that's going to depend on omega 0 and hs, omega 0 and hs plus 1, omega 0 in hs, and the difference between omega 0 minus omega 0 prime in hs. All right. The loss of derivative here is very standard for the Euler equation, right? If I do a difference, there will always be like an extra derivative that falls on one of the solutions, and this is why the Euler equations are quasi-linear. You have to pay one derivative to get the Lipschitz estimate. But then on the flow, we have a better estimate, phi t minus phi t prime in hs. Right, because the flow is being determined from the velocity, which is one derivative better than the vorticity. This is going to be smaller than, of course, there are constants here. The constant is going to now depend on the hs norm. And the difference, though, here is in hs minus 1. The key thing here is that there's one derivative discrepancy here, derivative gain. And what Koch observed is the following. Again, it's my language, not his, but is that the stability of Euler flows by high frequency perturbation. If I inject a very high frequency perturbation, the Euler flows will stay close. More precisely, so what is really happening? So this shows the following. If I take F0 is omega 0 plus delta S minus 1 eta, eta is a smooth fixed function by eta. And this is exactly the scaling in 2D to conserve the HS norm. And I will gain between flows a factor delta for this kind of perturbation. I'm going to show how to exploit this to show the Euclidean instability. Let's just take, so for me, just S is going to be an integer for the next computation, just to make everything clear. The Faddy-Bruno formula states the following. If I take the S derivative of F0 composed with the inverse flow, then I get S derivatives on F0 composed with the inverse flow. And this is being applied to the differential of the inverse S times plus a residual term that is only going to depend on F0 HS minus 1 and phi t HS. And the idea is that by taking eta in this form, this you might get a huge constant here, maybe a double exponential one. But you have this factor delta in front. And then when S derivatives hit eta, I get something of order 1, right? So here, ds of eta, this is going to be of order 1. Minus 1. Then I have the flow here. This is much, much bigger than 1. This is the hypothesis that we said we assume that the omega 0 has a flow that grows unboundedly. And so now I choose delta to control this term, make it small, and I choose eta to pick up the growth. And that's the Koch argument. And so I've showed point 2. And now how does one prove point one? What is the real physical phenomena driving growth? The idea is if you are in R2, say you have some vorticity here, compactly supported, so particles are turning, and there are some particles there at plus infinity. So you have people just turning all the time around zero, but particles at plus infinity are not moving. So if I somehow draw an imaginary infinite line, it becomes even more and more infinite. Of course, this is not rigorous. Let me show you how to make such an observation rigorous. And this is due to some a diagonal functional on R2 that is due to Shankar. I think Jan would like it very much. So if you take omega 0 that's C infinity compactly supported, there is Shankar's identity. It goes as follows. So if we define g of t as the integral on R2 of u composed with phi t, dotted with phi t minus x plus gradient x of phi t. This is the integral over R2 of this scalar product here. Then the identity is d over dt of g. So this is I'm not going to get into it because I have other things I'd like to talk about. It has to do with the mouvement cinétique. U0 and L2. So the time derivative of g is 2 times the L2 energy. And from this, with Thomas, so this is the Shankar identity is this. Again, he doesn't write it this way. It's actually pretty impressive. It's a work he did in 2016 when he was still a bachelor in bachelor's, a bachelor student. Impressive, but right, he does it like he's a geometer, so nothing is rigorous for us. They are very rigorous. Just for us, in analysis, we like estimates. And the idea is that if you do that, well, of course, omega 0 is infinitely compact supported and zero average, but that's not important now. So from this, we were able to conclude with Thomas that we have the following inequality, that the RDR C squared is bigger than omega 0, U0, and then 2 E squared. I actually need to say that omega 0 is your average, because if not, the L2 norm of U is not guaranteed to be well defined. And so, and Xi of t is just phi t of x minus x. So this is almost the L2 norm of phi is blowing up. So Xi is just phi t of x minus x. Because phi t of x is not a vector, right? This is a vector, geometrically speaking. So R2, well, there's no problem there. And so from there, you can show that on this identity here and then this identity here, it's not too bad to show that the supremum of d phi t and infinity is equal to plus infinity. This is true for any omega 0 that is C infinity compact is supported in zero average, which yes is pretty large class. Hence answering the question of density and proving the Udovich conjecture on R2. Before I continue, let's take a second to see if there are any questions to discuss. We're good?
It's radial.
So say again?
If omega 0 is radial.
Yeah, then everything is actually exact.
Gradient of phi t.
See, if omega is radial, right, it's a steady state. A really good question. So omega of 0 of r, this is what's happening. you get U, so you get C of R. Nu would always look like this. So this is going to be 0 and dr psi, er e theta. But see, d over dt of phi is u composed with phi, right? And the motion is always happening on the level sets of the stream function. And as soon as you have two different angular velocities, the Lipschitz norm has to grow of the flow, because if two particles start close, so actually this instability result near steady state were actually proven by Koch. For Hamiltonian vector fields, it's the result is pretty direct. The whole thing that's really hard about this is that the Euler equation is a nonlinear evolution equation. So guaranteeing growth for all time is a tricky matter. When we were on S2, in symmetry, we fixed points that caused growth. On R2, there is this imaginary boundary at infinity. On a domain where Udovich did his work, you had particles that are on the boundary, stay on the boundary for all time. So you have stagnation on the boundary, and this is how they prove it. And this very good question brings me to my next point. What happens if I can no longer cheat? What happens on T2? There is no boundary, there's no infinity. How can I prove consistent and persistent growth in the fluid? Okay? Any questions? All good? What happens on the torus? Now I can. There are no hidden Lyapunov functions that I know of. There might be some smart ones. I don't know what. We work on the torus. On the torus, right? The vorticity. Where's this force? Also on this. The vorticity is like some graph over the torus. And because the vorticity is in HS bigger than 1, right? It has a minimum. Let's just suppose S is bigger than 2 for this discussion. Just gonna try. So the point now is try to identify the physical phenomena. One physical phenomena I can control to drive growth in the fluid. Okay. On R2 I was able to. On the sphere I was able to. In domains with boundary. Now on the torus, the idea is, let's suppose that omega 0 has a minimum, a unique minimum. M0 at x0. And it's non-degenerate.
Excuse me.
Yes.
So you don't have this identity here. The Shankar's identity is not true on the torus first.
No.
No,
I just like they have an RDR.
Okay.
It's very hard to have an RDR on the torus. But there is an analogous identity. You could look at what he did and try and do it by hand. Just the proof is so much simpler than what I'm going to show you right now. And you see that there are boundary terms, things don't close. OK. Si vous voulez, ce qui se passe vraiment, c'est que sur R2, il existe des champs vecteurs de divergence constante. There are no constant divergence velocity fields on the torus because of Stokes form, right? Or the divergence. That's really what's really happening behind this identity. That's why it's impossible on the torus. Okay. It's non-degenerate. So what's the picture? So the picture is the following, right? You have omega 0. And so this is the graph of omega 0 over some local chart on the torus near x0. And omega of t is omega 0 composed of the inverse flow. And, right, I can suppose by contradiction that, let's just suppose that this thing is bound. Because if it was not bounded, everything I already presented with the Koch would be done. So if this is bounded for all time, because omega t is omega 0 composed of the inverse flow, this non-degenerate minimum is actually a non-degenerate minimum for all time, right? The only way for it to degenerate is for d phi t to go to either infinity or zero. But there is the only way through this community characteristic is for this to blow up. So what I'm guaranteed is that, of course, M0 is always a minimum because omega is being transported. So omega 0 is always a minimum at phi t over x0. So M0 non-degenerate for all time. But if it's not degenerate for all time, right? The level sets of the vorticity are being conserved, then here particles go at very different speeds. And so there will be persistent shearing for all time. That's the picture. That's what should be happening at the minimum of the vorticity. If the vorticity does not average out or degenerates, then I should still shear more and more and more and more. You could ask me, so spoiler, this is the last 15 minutes, there will be micro-local analysis. So you can ask me, why are you doing this? Why are you not just doing this by hand? I'll tell you why. It's because suppose that you know why it's making this physical picture is so hard, like making it previous is so hard. At the minimum here, right, the vorticity, let's say x0 is 0, is like r squared. The stream function is equal to the vorticity. So the vorticity controls things in C like that are like R4. This is what the vorticity controls. So the minimum controls things that are like R4. So on the velocity, I'm controlling things that are like R3. But then locally, right, I still need to handle R and R squared terms. The 0, 1 is just calculus. But those, if I'm doing a Taylor expansion, I'm saying omega has a non-degenerate minimum. So it's like R squared. This equation here locally will only give me something like R4, right? And then, so because C, U is range orthogonal with C, to give me things that are like R3 in velocity. But the R squared terms are completely being determined by the non-local part of the Biot-Savart law. This is completely non-local. Non-local part in the BS law. So even though the picture I have in mind is that this shearing is always happening, if the equation was linear, it'd be done. But here the equation is really non-linear. You cannot, of course, I cannot like this happening, but you cannot just simply exclude the fact that the whole fluid is being adversarially pushing the particles against you and the R squared non-local components to ruin the growth that should be caused by this R cubed terms. So if you just try and do it by hand, you give a local chart, you give action angle coordinates and try and do it, you see you only get lower order terms that you can control. The leading order ones are completely non-local. And in the last 15 minutes of this talk, I'd like to explain how you can overcome those kind of problems. And for this, I am sorry. No, I'm not sorry. I actually like it a lot. We're going to have to do a micro-local list. Well, it's escalated for me. So theorem. I'm going to announce it for S bigger than for an integer because it's simpler. So this is again, of course, the map. And that's it. So the set of omega 0 in HS such that the supremum time of omega t HS is infinity is G delta in HS. Well, this establishes the Ljudovic conjecture for S bigger than 4. There is a gap between 1 and 4. One day, I hope. Good. But a really nice consequence of this that was proposed to us by Patrick mentioned, and we were able to do. He always mentions very interesting questions that like take 3 weeks for me to answer, and they are fun. It's the following. This actually implies that in the set of omega 0 of smooth vorticities is a very categorical type argument. So that there exists an n, so the supremum in time of omega of t in HM is infinite, is G delta. and you see infinity of the torus. Of course, here you have the natural Fréchet deformation. So you start with a smooth vorticity and generically a finite normal one. I'm not going to get into how to prove this, but here's a consequence of the theorem. And now I'm going to explain the ideas behind proving the theorem. So we've identified the physical phenomena. Now we're going to try and leverage it to make it into a proof. The first thing to do, so there are two ideas. The first one is to prove the following dichotomy. So the first thing to prove is either d phi t in L infinity grows unboundedly, or the HS norm of the flow grows unbounded. The first thing to do. So this is the Lagrangian instability part, right? The Lagrangian flow. So this is going to be true for a dense set of omega 0 in HS. The first thing to prove. Suppose this has been proven. Suppose someone again came and gave you this for free. This someone is very generous. The second thing to do is to prove the following: is if once you have this, then either the supremum, then what you prove the next one is either this thing blows up, or for all r strictly positive, for all thresholds n, there exists an F0 in the ball such that the vorticity went above the threshold. This is the second thing you want to prove. And I'm going to explain really quick how to prove this before I really want to try and talk about point one real quick. The idea to prove 2 now is different than the other one. You suppose that this stays bounded, so you get that the HS of the flow grows, right? So let's look again at the so the idea is we look at the Fadi-Bruno formula. Again. But now we suppose that this is bound. We suppose that this is not true. We suppose that this is not true. So which term would cause growth? What we did with the Koch instability, we used the first term. When all the derivatives fell on F, but only one derivative fell on the flow, and then we used the Lipschitz growth of the flow to conclude. Now, we will of course use the other one. all the derivatives fell on the flow. So ds of F composed of the inverse flow. So the term that will be interesting for us is this one. It's going to be df composed of the inverse flow, F0, sorry. Inverse flow. And then it's going to be now all the derivatives fell on the flow. Okay, plus other terms. Don't forget about for now. And under the hypothesis that this stays bounded, this thing grows, right? And the idea is, you want to pick up the growth of this, you want this thing to be like 1. So you want this thing to be like very low frequency, constant equal to 1. Right? In the Koch argument, we used a very high frequency perturbation. Here, we're going to use a very low frequency perturbation. What do I mean by this? We're going to do just a 1 mode perturbation of omega 0. And then we're going to, what you do, I'm not going to get into the details of this, you proceed, but you try and do a contradiction argument. You suppose by contradiction that the flow solution map stays bounded in the whole ball. Okay, there is a whole ball of initial data where no growth is happening. Right? Of course, this is extremely improbable. And what you do is, because you use only this very low frequency perturbation, you say, okay, if in this whole open ball I have no growth, then say I perturb everything with cosine x1. Because it's cosine x1, I can perturb it in a way that I always stay in the ball when I perturb it, then use a Schauder fixed point argument to get a contradiction. So a topological argument for the contradiction. A contradiction argument prove Shelburne experiment. So this is in some sense the other end of the instability to Koch. Now let me prove point one. So now I hope I've convinced you or not that in order to show Eulerian instability, so instability of the vorticity, it suffices to show instability of the flow map, either the Lipschitz one or the S one, and either through the Koch argument or the topological argument we give with Schumann. And how do we do this? The idea is, so how familiar are the people here with the paraproducts and Fourier multipliers? So it's good for everyone? Let's just real quick that the idea between, so for paraproducts, Fourier multipliers, I strongly encourage you to read Raphael and Hager's book with Jean-Yves about all of this. It's extremely clear, and it's very simple. So the idea is that you want to break up two functions, the product of two functions, into three terms that morally will have the same regularity of G, the same regularity of F, and some term that has the regularity of G plus the regularity of F. How do you do this? There are some funny formulas by Schneerman where you can do it by hand, but the clean way to do it, the best way to do it, in my opinion, is to go through little Rayleigh projections. And again, I strongly encourage you to read Hager and Raphael's books. Well, I'm going to suppose this is known. I'm going to introduce one extra thing that's not really in the book, but they do composition estimates in the book. Something called paracomposition. So this was pioneered by Schneerman in the 90s. Sorry, by Alignac in the 80s. Sorry. By Alignac in the 80s. By Alignac in the 80s. So I'm going to just define this like this. It's a definition. It's just a definition. You can say, why do you define this very weird definition? If you look at the book by Raphael and Hager, you will see that this is the Boni linearization theorem in the composition. And I'm just somehow extracting the other term and calling the other term the paracomposition operator. It has exactly the same kind of properties for paraproducts. That is, this term has the regularity of F, this term has the regularity of chi. But I'm not going to get into it. I'm just going to define it this way. I just need it for the algebra. I don't need it for the estimates. And the idea is the following. It's the following unknown due to Schneerman. The Schneerman unknown is that we want to understand the evolution of the following. So we call the d over dt of phi t is u composed of phi. I think it's going to be time in like 5 minutes. Please stop if I go over. The idea is to study the following unknown, x of t is t over d phi t minus 1. I've been working on this unknown for like 4 or 5 years, and for my absolute disappointment, I have no good interpretation, physical interpretation of this one. Works magically well. I do not have a good physical image. I have a very good image of what it does analytically, frequency space, etc. But I have to say, I don't have a good physical interpretation for you. Sorry about that. But it is a funny unknown because it has been used independently without knowing in many different works. There is, if you work in waterways, there is the good unknown of Alignac. There's actually a variation of this one. If you look at, I've talked a little bit with David. David, when he works also with those special unknowns, he needs the special choices of variables. It usually always gets back some sort of variable like this. Now I'm going to explain why this is interesting. I don't have a good physical interpretation of this. The only thing I can tell you is equal to the identity minus the paracomposition of the flow with the inverse flow. So of course, regularity-wise, the identity, we don't care about it. It's an analytic function. So one physical interpretation is that somehow we're pulling back the inverse flow to the original frame, but only in the crude scales. And somehow this breaks the symmetry, and there's something interesting that happens. So the only physical interpretation I can give you is the following. The time derivative of xt, you can show it's equal to the following. Plus r. Anytime I write r now, it just means a smoother term. So it's an r in the sense of macroeconomic analysis, so it's a smoother term. And now we can try and look at this thing and try and understand what does it really mean. It's a pretty intriguing formula because let's just write it differentially. Differentially, it would look like this. But this is just the fullback of u by phi. Right? So this is the para pullback of u by phi. This is the para version of the pull. U is gradient orthogonal of psi. The magic of incompressible fluids is that this is equal to the gradient orthogonal of the pullback of psi. So you could show that this is equal to the gradient orthogonal of phi t star psi. And something really striking is that the residual term here is completely explicit. It is d phi t minus 1 u composed with phi n. I know this doesn't seem like much for people who are not used to microeconomic analysis, but I just fully, so take any Lagrangian flow, forget about the Euler equations for now. This first identity here works for any flow you want. This completely parallelizes the flow. Regularity-wise, I completely parallelize the. See, this equation here is very hard to study regularity-wise. This one here is much faster, regularity. The same thing here. But of course, so this is what Schneerman did, and that I revisited 4 years ago. And of course, if you do PDEs, you really like an equation that's only on this variable x, right? And if you compute a little bit, you get the following equation. Work a little bit harder. What I did. You realize that the closed equation you get on x is the following. So, right, psi, Laplacian psi is equal to omega. And so, if I write phi t star of Laplacian psi is equal to phi t star of omega, right? And I want to commute, I want to put a composition inside of a Laplacian, and I just get the Laplace Beltrami operator. So I get the Laplace Beltrami operator of phi t star c is equal to phi t star omega plus r. This is not so weird. If it was standard composition, the object you get here to leading order would be d5 minus d5. This is the Laplace Beltrami operator by the flow by the diffeomorphism phi. I don't know it by heart. I just prepared my notes. And of course, here this is the paradifferential version. So it's just going to be like this. Here's the paradifferential version. And so I can write phi t star psi is equal to a parametric of the Laplace Beltrami operator inverse applied to omega. Again, this Q is nothing scary. Q is simply the paradifferential operator with the following symbol. So it's square. It's of order -2, and you just have to, of course, change the axes of frequencies depending on the chain of variables. And then to conclude, right, we're going to write omega of t composed with phi t is omega 0. And from there, you can show, should you break with paracomposition, get that phi is equal to omega 0 minus dot x of t plus a residual term. All of this to give the following equation: dt of x plus gradient orthogonal of q t gradient of omega 0 x of t is equal to gradient orthogonal of q omega 0 plus the residual term. I went above the time. I'm sorry. I'm just going to conclude on this. Except if you give me 2 more minutes, I can really explain how to conclude. But I can be annoying to everyone.
We're gonna para-decompose the audio.
Yes, I'm going to paradecompose that. So this equation, I'm just going to mention it. It's due to this equation that you can prove that the HS of norm of the flow grows. 4 years ago, I was able to show that the HS plus 1 norm of the flow grows. But this was not enough, because if you do the Fadi-Bruno formula, if the HS plus 1 norm of the flow grows, it tells you nothing about the HS norm of the vorticity. You really need to get to the threshold S. And you really need to observe a cancellation here. It's not so easy to observe. You have to use cusps and so on. But I do really like this equation in the following sense. Just forget about my result. Here's a very funny result about the Euler equation. In the 90s, Philippe Sefrati and Jean-Yves Schumann developmentally showed that the flow depends analytically on time. Right? There is analytic dependence on time, right, for the Euler equation. And the proof is pretty involved. But I claim that if by just looking at this equation, you can prove the same result in those 10 lines of computations. Of course, I'm cheating because I'm using power differential. What is the order of this operator here on x? This is of order -2, order 1, order 0. This is of order -1. This is a force. This is the vorticity. This is driving the fluid. Q depends on the Lipschitz norm of the flow, so it's just one fixed norm. And then you have the gradient perp here. And so you have something that's order -1. So this is a PDE with something of order -1 applied to x with a force here. And so immediately you see that x has to analytically depend on time. And if x, which is just a renormalization of flow, analytically depends on time, you get the same thing on the flow. It's a beautiful result in the 90s. And you could just see it through this. Here's what I'm trying to say. This unknown is very interesting. Thank you.
Les questions?
En français?
Oui.
Sur les résultats à la Baire, en général, il y a ce genre de G delta, et on sait aussi montrer des exemples explicites. Est-ce que là, dans tous les HS, on sait faire ça? On a
Un exemple,
il y a données initiales qui génèrent en temps infini.
Oui, bah, tous les états stationnaires le font déjà. Ça, c'était connu.
D'accord, mais pas. Okay.
Mais le problème, c'est.
Dans l'infini, on n'a pas une dynamique qui évolue.
Bah, il y a la dynamique sur S2, il y a la dynamique des scale invariant solutions, il y a les spirales logarithmiques. Mais mais en général, la dynamique la plus claire, c'est celle donnée. Enfin, le théorème de ça, il dit la chose suivante. De manière générique, localement, le champ de vitesse, il va ressembler à quelque chose comme ça. Et parce que les points critiques sont rares. Et donc, génériquement, en fait, il se faut que il y a le phénomène de cisaillement dans le fluide. Tout le problème, c'est comment maintenir ce cisaillement de manière persistante pour tout temps. Parce que je peux cisailler comme ça pour un petit bout de temps, ensuite cisailler dans l'autre, ensuite re-cisailler là, complètement ruiner tout ce que j'ai cisaillé. Voilà. Donc, le phénomène physique est très clair. C'est juste des lignes de niveau qui bougent, des particules qui vont bouger sur des lignes de niveau à des vitesses différentes. Okay. Comment maintenir ça pour tout temps? Voilà. Moi, je l'ai donné dans le cas du minimum.
D'accord. Tu dis qu'il y a des exemples explicites et je veux
Oui.
Donc là, la remarque de Patrick Gérard avec le raffinement que tu ne nous as pas détaillé,
oui.
Tu l'as écrit là-bas, ça dit que même quand on a un truc très régulier, c'est infini, oui. On va avoir un exposant pour lequel ça va dégénérer.
Oui.
Mais on s'attendrait à nouveau pour ce genre de berrerie là, si on paye suffisamment, peut-être en demandant à ce qu'elle soit analytique, Alors, on est sûr que ça n'arrive pas? Non, c'est pas vrai?
Donc, j'aimerais, ça marche. Je peux vous le démontrer. En analytique, je ne peux pas. Là, c'est un peu cher.
D'accord.
Je ne saurais pas. Déjà, parce que tout ce que je fais ici, je ne suis pas réellement. Tout ce que je fais ici pourrait marcher dans GVR, mais en analytique, c'est vraiment l'ennemi. Parce que l'ennemi, il est assez facile à voir.
Mais je demande dans l'autre sens. Hein. Je demande une condition suffisamment forte qui fait que ça n'arrive pas.
Ah, en analytique, ça n'arrive pas. Non, vraiment.
Non? Ok.
Je pense pas. En fait, déjà, je pense pas que c'est vrai, mais ouais, je pense que ce n'est pas vrai. En fait. Je pense que même dans l'éthique, ça a lieu. C'est juste toutes les techniques qu'on a, c'est pas arriver à ce niveau de la régularité.
Ouais. J'ai une question qui est un peu la suite de la première question d'Ayman. Tout à l'heure, dans les dessins que tu avais fait, où il y avait des petits filaments de sportivité qui s'aggloméraient en temps grand et qui faisaient des tourbillons, et vous aimez les structures de topologie et voilà. Est-ce qu'on a des exemples explicites ou de solutions qui ont exactement ce comportement-là, où du coup, j'imagine que des gros tourbillons, justement, ils sont cisaillés, comme tu disais?
Les gros tourbillons comme ça,
Ouais.
ça c'est complètement ouvert. C'est extrêmement dur. La seule, enfin, extrêmement dur, je sais pas, mais dur, extrêmement. Mais les seuls exemples de flow avec un phénomène de cisaillement où les choses ont été démontrées, c'est uniquement les trucs de l'université.
Ouais.
Donc le plus simple, c'est quoi?
Oui, oui.
Mais c'est tout. Même pour une poche radiale, c'est ouvert. Il y a une VCDR proche d'une poche radiale, c'est pas connu. On sait vraiment le faire que dans ce cas-là. Et les variations de ce cas-là, monotone, etc. Et là, on arrive à le faire parce qu'on arrive à étudier super bien le linéarisé, le spectre, et on bataille avec. Et ce qu'ils font est très impressionnant. Hein, mais même dans ce cas, c'est pas très. Là, la théorie linéaire dans celui-là est encore. Ça demande beaucoup. Donc, non, ce serait incroyable si on avait ce genre de résultat un poil d'un page. Mais c'est un truc qui me vient à l'esprit, c'est les résultats de TI Galé, par exemple avec Michael et Gauche, mais c'est sur Navier-Stokes en fait, et donc c'est différent. Et c'est sur des solutions particulières, c'est jamais sur un ouvert de solutions.
Non, mais déjà avec une solution particulière, tu vas déjà avoir une description possible d'un mécanisme.
Ah, bah, si c'est juste une solution particulière qu'on fait.
Il y a un temps infini, comme tu disais. C'est pas juste une description sur un temps transient, c'est ça?
Là, les seuls résultats que je connais, je pense qu'ils sont existants, c'est soit des solutions très spéciales, ce qui est un peu le projet de recherche de Zeynep Hassini, qui est vraiment à Grenade. Et là, il peut leapfrogging, des choses comme ça, mais c'est des solutions qui font ça, qui parlent de solutions de vortex, qui désingularisent, qui obtiennent ces solutions-là. Et il y a ensuite, c'est souvent en partant de solutions de vortex qu'on désingularise, ou sinon, voilà, on essaie de démontrer pour des temps longs, mais jamais des temps infinis. Je pense que j'espère que je ne me trompe pas, mais je ne pense pas qu'il y a des résultats connus. Ça serait super bon.
Et toutes ces solutions-là là, dont tu parles, donc c'est effectivement le flow, il explose, enfin, si on regarde le granulat du flow, mais la vorticité, elle, dans ces cas-là, elle reconverge vers un truc.
Elle est même stationnaire. Là, la zéro
oui, mais disons, quand on prend des perturbations, elle peut reconverger. Donc finalement, tout est dans ce truc de corps, là, c'est ça, il dit, je peux trouver, si j'ai un truc où le flow diverge, alors il y a une vorticité proche qui, elle, va merder aussi.
Oui, c'est ça. En fait, si tu veux, là, c'est le poor man's version de la turbulence. La turbulence, ce serait de montrer que je perturbe ça, et ensuite, ça va se moyenner en temps infini, je vais avoir une convergence faible dans L2. Moi, tout ce que je dis, beaucoup plus pauvre que ça, tout ce que je dis, c'est qu'en fait, les normes positives, qui sont quand même des normes extrêmement strictes, explosent en temps infini. Des normes aussi larges que L2, qui vont contrôler des choses comme ça, de manière générique, comme ça, ça revient à la conjecture que je verrai chez Ayman, et cette perte de capacité de mixing générique, on est complètement, enfin, c'est très loin de ça. Évidemment, on vise, au fond, on est très très loin de ça.
Est-ce qu'en ligne, il y a des questions?
Oui, j'ai une petite question, s'il vous plaît.
Ah, bah, une question de Fatma.
Oui.
Bonjour.
Bonjour.
Allez-y, je vous entends.
I didn't. Thank you very much for your talk. I joined it a bit later, but I want to know, maybe I missed what you were talking about. The loss of regularity, was it depending on the parameter of delta or?
No, that G delta means just generic in the bare category sense. It's just the notation.
All
Delta
right,
is
okay.
just a notation. It just mean G delta dense. That's the, yeah.
All right. So delta is not a parameter that we should have it as an optimal, or it doesn't have to do anything with the loss of regularity, no?
No. It's just a way of quantifying in infinite dimensions what generically could mean. No
Thank you
problem.
very much. I enjoyed it. Okay, anyway.